we had to go up to speed with the lectures at that time. The lectures for 10 and 13 are recorded lectures. They're just going through their post-processing phase. And so they'll be up there by Monday, and we'll use those, not next week, but the following week, when we get stuck into
so we're running a
revision to the mid-semester exam. We'll talk about the assignment, and we'll do those tutorial problems, chapters 10 and 13. By that stage, we'll have everything necessary in order to prepare for the mid-semester exam, which will be held in that first week there. I'm not quite sure what date yet, but I'll double check on that before. It is 15th already. Okay, that's good. In the past, some people have mistakenly thought it was a class quiz, and they've turned up here, or the equivalent room, and to find nobody home. So we don't want to do that. It's a centrally conducted exam. It'll be wherever they find accommodation for you. And okay. Before we put the tutorial problems on 7, 8, and 9, has anyone gone back over any of the previous problems and want anything double checked or clarified before we move on? If you haven't done that yet, no big deal, because that's precisely what we can make sure happens on the 10th, in our revision for the mid-semester exam. So any little gaps amongst your collection of diligently solved problems, we can plug up then, if not useful. All right, so chapter 7, which was about deadlocks, and then our problems there from the 8th edition, 714, 715, and 720, with equivalents in the 9th edition, and the hybrid 8th edition, bastardized 8th edition, whatever it is. In a real computer system, neither the resources available nor the demands of processes for resources are consistent over long periods, in brackets, months, perhaps even days. Resources break or replace, new processes come and go, new resources are brought back into the system, deadlock is controlled by the banker's, if deadlock is controlled by the banker's algorithm, that was where we finished last week, because we didn't know what we're dealing with the banker's algorithm. If resources are controlled by the banker's algorithm, which of the following changes can be made safely, including, which presupposes we know what a safe state is, that's defined. Which of the following changes can be made safely, and under what circumstances? Okay, so a few things to ensure we've got clear before we start looking at a solution for that. What's the banker's algorithm all about?
Not giving up resources if you can't complete the job.
Yeah,
sort of.
That's right, pretty much. It's a deadlock avoidance strategy. It's saying there were 4 criteria that we could identify that could lead to a deadlock occurring, and the banker's algorithm attempts to come up with a strategy for avoiding a deadlock by keeping in reserve enough resources to satisfy at least one processor's possible request. Now, where is the practical limitation in doing that, do we think? It sounds all right. We keep in reserve, the operator keeps in reserve enough resources to satisfy satisfy at least one of the processes that's running their maximum resource request. Where's the physical, or where's the practical, not physical, where's the practical limitation in that strategy?
You have to know how long each process is going to run for?
Yeah, you have to know in advance of the current time all of the possible future resource requests you might make. So we have to know at time t, we have to know all possible requests that all processes are going to make, the resources in the system. And that, unfortunately, points to an unrealistic requirement
Expanding bankers
for most computer systems anyway. There might be some specialised ones where that can be made to apply. Some specialised computers that only run a certain group of processes all their lives, all their operational lives. And if that group of processes is well known, then the administrator might be able to determine beforehand what resource requirements all the processes will ever need. But it's not a realistic requirement in most modern human user-oriented reprogrammable computer systems, like PCs and workstations and whatnot. All right, so that's what the bankers algorithm is about, and that's the fundamental limitation that it has on it. What's this safety business? A safe state, that gets defined. Well, if we've got our bankers algorithm managing resources in such a way that it does always ensure that it keeps available enough resources to satisfy at least one process's maximum request, then it's deemed to be operating in a safe mode, a safe state. And whenever it's operating safely, we can't possibly have a deadlock. That's nice. Can't possibly have a deadlock. It doesn't necessarily mean, though, that we must restrict the system to always operating in what's called a safe state. Occasional departures into unsafe states might not present an operational problem. Not a real good idea to stay there very long, but there might be some occasions whereby an unsafe state can be exhibited for a short while, and we won't get a deadlock as long as we move back into a safe state again sometime soon. All very rubbery. Okay, well, now that we know what bankers algorithm is all about, and we know what safety is, we should be able to answer these questions. Increasing the available vector. Is that likely to move us from a safe state into an unsafe state? That's what the question's asking.
No.
I don't think so, no. Because what's increasing the available vector actually doing?
It allows you more resources to allocate.
Yeah, that's right. We're doing things like adding more memory, or adding more peripheral devices, or adding more processors. And that's, of course, not likely to cause us any operational problems in terms of system safety, adding to the available vector. What about decreasing the available vector?
Yeah. Yes.
Yeah, quite the opposite. We can have budgeted for all the resource requirements that the processes have and maintain enough in reserve. In other words, we're applying the safety policy properly. But if someone comes along and starts removing resources, then that's actually shifting the goalposts on us pretty severely and won't do anything positive to maintaining a safe state. So most definitely, decreasing the available vector is not a good idea. What about increasing the max requirements for one particular process? Not all of them, but just one of them. Increasing the max for one process.
It depends on the other processes, doesn't it?
Yeah, it's not quite so clear cut. It doesn't help with safety. It doesn't help. It doesn't necessarily mean we'll get a deadlock, but increasing the maximum requirements for one process, it doesn't help the safety at all. It might actually turn out that that max increase requirement, or max increase in the requirements, that might actually turn out to be more than the system's physically got available, which means that process is going to stop. So that's not going to help. That's bad for safety. What about decreasing the max for one process? Yeah, that's right. That's not going to hurt safety. What about increasing the number of processes?
Increasing? No, that would.
It depends on the max, doesn't it?
Yeah, that's right. It doesn't impinge on our safety requirement, increasing the maximum number of processes. It doesn't. We still stick to the policy. It doesn't matter if there are more processes in the system, we still stick to our policy of reserving, keeping back enough resources to satisfy at least one process's maximum requirements. If we add more processes, it just means that some are going to have to wait longer before they get what they want. That's tough luck for them. So that doesn't take us from a safe state to an unsafe state, increasing the number of processes. Even though at first glance we might think it's not good. All right, decreasing the number of processes. That, of course, is not going to hurt our safety algorithm at all. Not going to make things any more difficult for us.
Couldn't you lead to like cycles and stuff? Start removing things? Or?
No, I think it just means that it's easier for the banker's algorithm to keep enough resources in reserve for at least one of the processes. If it's got less processes to worry about, it relaxes the constraints quite a lot. In fact, decreasing the number of processes, selecting processes to kill, is one way of dealing with deadlock when it does occur. Rightio. So the short answers were: increase new resources, not a problem. Decrease resources, that is a problem. Increasing the max for one process, that is a problem. Decreasing the max for one process, that's not a problem. Increasing the number of processes, not a problem. And decreasing the number of processes, not a problem. The reason that we are 7:15. Consider a system consisting of 4 resources of the same type that are shared by 3 processes, each of which needs at most 2 resources. Show that the system is deadlock free. Okay, what's the best way to approach this? 4 resources of the same type that are shared by 3 processes, each of which needs at most 2 resources. Show the system is deadlock free. What tools will we use to solve this problem? I'll give you a hint. It's not the banker's algorithm.
It's the resource.
Yes, that's right. It's the only other tool that we studied in Chapter 7, the resource graph. All right, so let's draw resource graphs. Yes, mate.
It's the resource graphs because they're all same instances, right? Same number of instances.
Actually, it's a resource graph just because there aren't many resources altogether.
Okay.
Ordinarily, though, we would use the banker's algorithm if we've got multiple instances of lots of resources. And that's sort of what they're suggesting here, unfortunately, yeah. So this time around, we'll use the resource graph just because there aren't very many instances. In fact, when you have a look at the solution, it doesn't matter whether it's 4 instances of resources of the same type or whether they're 4 different resources.
Okay.
So that provision they put in the question is a bit of a red herring. All right? But that's a good question. Yeah. Ordinarily, when we get multiple instances of a resource type, we start thinking about this number. All right. So we've got 4 resources. Let me show them as lots. And we've got 3 processes. And each of these processes requires, at most, 2 of the resources. And with these resource allocation graphs, we show arrows, directed arcs they like to call them, between the resource and the process, indicating whether or not the process is requesting the resource or whether it's holding it. That changes the direction of the arrow. All right, well, if we've got 3 processes, they each want 2 of the resources at most, then the different possibilities that we've got are this one has been requested and been granted 2 resources. That's one possibility. Another possibility is that resource has been requested by that process and granted to it, and that one requested by that process and granted to it. So there's one possibility. Here's another one.
Start liking it. Why?
3 processes again. Each of them's got 1.
Basic gentrification.
Oops. There's another possibility. Are there any others that are more complicated than that? There's quite a few possibilities that are simpler than that. Are there any that involve most or all the resources being allocated at any one time? That's the interesting thing to consider here. Yes, 2 of them hold 2. That's right. 2 of them hold 2. Let's do that. All right. Now, in all of those scenarios, we can argue that by inspection, the system's deadlock free. Why? Sorry, no. Yeah, that's right. We've got no closed loop. Remember, in the earlier part of Chapter 7, where they were describing using these resource graphs, direct resource graphs, resource allocation graphs, they were saying, whenever we've got a closed loop, some path we can find, arbitrarily on text diagram, if we can find some path where we can go from resource to process to resource to process to resource to process to resource to process, blah, 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 around in a loop, following arrows from head to tail, or tail to head, if we can follow them all in one direction around in a loop, there's a possibility of deadlock occurring with that. It doesn't actually mean deadlock has occurred, but it means that there's a possibility of deadlock. So it's these closed loops of allocated resources to processes that are the problem. There's one example there. Right. That one shows a resource allocation graph with a deadlock, because we can see that there's a closed loop involving R2, P2, R3 and P3. That one involves a deadlock. But this one doesn't, even though there's a closed loop in it. Why does that one not involve a deadlock?
Is it sequence you can follow?
Because it's a cycle, not a...
Well, yeah, but I mean, there's a closed loop there, but there's no deadlock. Why is that?
P4 could eventually be done freeing up.
Yeah, in fact, one of the requirements, yeah, that's right, one of the requirements is that when a process gets access to a resource, it doesn't hold on to it forever. That kind of doesn't make sense, having the resource holding on to it forever. And so it's an easy requirement to meet. When a process gets granted a resource, it requests a resource, it gets granted that resource, it uses it, and then it releases it. And so at some point down the track, we can expect both P2 and P4 to release resources R2 and R1 and R2 respectively, and therefore we won't have a deadlock, because P3 will eventually get R2, the second instance of R2, and P1 will eventually get the second instance of R1, and they'll all have what they want. Whereas up here we've got a deadlock. Because P1 wants R1, but R1's being held by P2, and P2 wants R3, but R3 is being held by P3, and P3 wants R2, but R2s are being held by P1 and P2. So everybody wants something that someone else has got without being prepared to give up anything they've got. We've definitely got a deadlock. Well, here we've got no closed loops. So that's reassuring to start with. We don't expect to see any deadlocks here. But beyond that, it's so simple we can identify that at least one of those processes will always run to completion. And what does that mean? Why is that a good thing? That's right, yeah. When a process runs to completion, it returns the resources that it used. So they go into the available pool. So top left-hand side there, we've got this process up the top here, P1. It's got 2 resources. That's all it needs. It's got all it ever wants. So it will eventually use those and return them. So these 2 arcs will disappear, and those 2 can be allocated to the other 2 processes. So obviously no deadlock there. Same deal with the diagram on the top right-hand side. Each one of them has got 1. That leaves 1 left over, which means that we move from this scenario here to that one, which we've already proven is deadlock free. The other arrangement is this one down here, where 2 of them have got 2, which clearly means they'll both eventually terminate and return the resources, leaving the last one, we'll call that one P3, to help itself. So, using a directed resource graph, we've shown that with the scenarios that are possible, none will lead to a deadlock. Nice and easy. Okay, next one, 720. (720) is a Banker's algorithm. Consider the following snapshot of a system. So we've got the allocation matrix there on the left, the maximum requirements matrix there in the middle, and the available vector on the right-hand side. So, at some instant in time, resources have been allocated to processes in the way that's described by that matrix there on the left. But, again, with the Banker's algorithm, we need to be able to look into the future, and foreknowledge gives us the maximum requirements matrix there. And what's left over after we've handed our resources to processes is the available vector, of course, and that's the thing we keep an eye on, because we want to make sure that there's enough resources in here, in the available vector, to satisfy the maximum requirements of at least one of the processes. Okay, the first part says, what does the contents of the matrix need? How do we evaluate the need matrix?
Get the max matrix minus the allocation matrix.
That's right. yj minus allocation yj. And we can do that, might as well. Write down these matrix. Okay. P0. That's a good sign to start with. P1. Two. P4. Okay, so there's our needs matrix. And I'll write available over here. Okay. Is the system in a safe state? Yes, it is. Why? Absolutely. Correct. We've got, in order for us to be in a safe state, we need to be able to afford to loan out from the available vector enough resources to satisfy the needs of at least one process. And that certainly is meant by two processes in the system, 0 and 3. So we've got a safe state. Okay, last part says, part C, if a request from process P1 arrives for 0, 4, 2 and 0, so we've got P1 requesting 0, 4, 2 and 0, can the request be granted immediately?
It can, but it shouldn't.
Yeah, it can, but it's not necessarily a good idea.
Because it's going to need more resources.
Yeah,
Not
it's going to
necessarily.
need more, so it hasn't actually got the...
It's going to need more for its max to complete.
That's right, it hasn't got enough to complete. So all we've done is to deplete the available vector with not much to gain, because P1 still won't be able to complete and return everything that it has.
It will also send it into deadlock because P2 and P3 hold the remainder. Of it,
Yeah,
of what you need.
yeah, that's right. What happens to the available vector? Well, let's consider what happens then. All right. So if we allow process P1 to have 0, 4, 2, and 0, so that becomes 11, and that becomes 7, and this becomes 0, 1, 0, 0. Even when P0 completes, what does our available vector then become?
What P0 currently is.
When P0 terminates, so it's gone. Our available vector becomes 0, 1, 1, and 2. That's not much chop, is it? No, it's not. Why? Sorry, mate. Yeah, none of them will now. That's right. We've sabotaged the possibilities for P3 to complete. Even though P0 completes and returns what it holds, we still only end up with this, which is not enough for P3 to complete, or P2 to complete, to say nothing of P1 and P4. So by looking into the future, we've been able to say, yes, even though we can afford to give P1 the requirement that it comes up with, 0, 4, 2 and 0, even though we can afford to grant that request in the immediate sense, looking further ahead, it's not a good idea to do that.
But actually, you're missing a 1 in column A for the available.
Missing a 1 where, mate?
In column A for the available, in the box. Because we granted 0, 4, 2, 0. So it should be 1, 1. Shouldn't it be 1?
Oh, yeah. I
Yeah.
think you're right, yeah.
Yeah. Because it doesn't request that 1.
No, it doesn't. You're right.
So
All right. Well, in that case,
P2 can actually
yeah,
complete.
P3 can actually complete. When P3 does complete, what do we end up with? We end up with 1, 1, 3, 2.
No, that one can't complete. Because you've got 1, 1, 1, 2 available and it needs a 2 of C.
Oh, yeah.
So P2 is the one that can complete.
Yeah, you're right.
So if you give it to P2, you end up with 0, 1, 3, 0. And then P3 gives back 2, 3, 5, 6. Oh, no. That's not right. 0, 1, 1, so you end up with 2, 4, 6, 6. So you can't actually pull it off, it's just really, really risky and really
Yes,
slow. So it doesn't go into deadlock, but
No,
it will slow down the system.
it goes into an unsafe state for a while.
Yeah.
Yeah, which, like we mentioned before, is not recommended, but occasionally it might be a useful strategy.
So would the answer to the question be yes?
You can, but you shouldn't.
Yes, you can, but you probably shouldn't. It just restricts your options afterwards if you do that. All right. Okay. 8.9. Explain the difference between internal and external fragmentation. What was that fragmentation stuff all about? All right, simpler question. What was it not about? It was not about file fragmentation on disk. It was not about that. That's normally where we hear the word fragmentation. In fact, that's the hardest part of this subject, working out that people aren't talking about what they're talking about. How did internal fragmentation occur? Well, remember, the stuff that we're dealing with in Chapter 8 is like old school memory management. And the way in which those processes used to be allocated memory was we'd have a linear array of memory locations. We'd section off a region for the operating system, and it would help itself to that when it initialised. And of course, no other process can touch that protected memory. And then the way in which it used to work with fixed partitioning schemes, fixed partitioning, was that soon after the operating system initialised, it would create these partitions in memory, maybe not all the same size, and those would be boundaries that it would maintain through the entire time the operating system is resident, and the entire time that the machine is supporting processes, running programs. And when a process wants to be created, when we want to load a program in memory and execute it, we find one of these partitions which will accommodate the process, and then we load it in there. Let's say it's this one. We load it in, and the small amount of memory which is within the partition, but not required by the process, is a region of memory which is unutilised while that process is in memory. And that's called memory which is lost due to internal fragmentation. So while this process, P1, is in memory, it requires only a certain amount of memory to be made resident, and the leftover space there is not accessible by it or any other process. So it's temporarily wasted memory. Internal fragmentation. The memory manager would organise which partition to allocate to a process when it was loaded in memory using some sort of selection scheme. Can we remember what some of those schemes were? There were schemes like best fit and first fit and worst fit, whereby the memory manager would search through all of the unallocated partitions and find one for the process which wants to be loaded based on a policy of some sort. The one which tends to make most sense is the best fit policy, whereby it looks at all the free partitions and it finds the one with the smallest amount of memory wastage due to internal fragmentation. But what makes that one, what disadvantage does that one have in runtime?
It should take more time.
What disadvantage does the best fit scheme have? Well, it takes a bit of time. We've got lots of these partitions. I've only shown 4 or 5 there on the diagram, but there might be several thousand. And if it's got to search through several thousand free partitions, looking for the one which is closest to, but not smaller than, the requirements of the process which needs to become memory resident, then we've got to search through the entire list and then come back to the best one. Yeah, it takes longer. Yeah. The alternative approach, the first bit, says let's just start searching from the first free block that we have, the first free partition. And the first one that we find is big enough, it doesn't matter by how much it is too big, that will do. So it's faster at runtime. But the compromise is more memory temporarily wasted due to internal fragmentation. Sorry, mate? Maybe. There are other schemes like this whereby the partitions, in fact, yes, that takes us to the next part of this problem. There are other schemes whereby the partitions are not created at initialization time, but the operating system boots up, gives itself a partition, and then it says, right, I'll create partitions only as necessary now, whenever a process gets loaded into memory, and I'll make those partitions exactly the right fit. So, as process P1 appears, a brand new partition is created, just exactly the right size for it. And then when P2 appears, a brand new partition created for it, just the right size. And P3, same deal. brand new partition, just the right size for P3, and we end up with how much internal memory wastage due to internal fragmentation? Absolutely zero. That's right. It looks like this is a real good move. Problem is, if P2 terminates and this partition now becomes empty, the biggest process we can fit into there, P whatever, when it gets loaded, is one that's the same size as P2 or smaller. And if we load a new one in there, which is smaller, then once again, we've got a new partition created with another very small partition left over. And we can imagine, by extending that scenario, that if P1 terminated and left memory, then once again the largest process we could deposit in there would be one which would be coincidentally exactly the same size, that's not going to happen very often, or smaller. So another process gets loaded into here, and we've got yet another partition, very small one, being created there. And we end up with lots of little tiny partitions all over the place, whose net memory constitutes a significant amount, but because they were scattered all over the place, we can't get access to, they're not big enough. Each individual one is not big enough to be useful to us, but their net total is significant. We end up wasting that amount of memory due to what's called external fragmentation. One solution to that is just about moving processes in memory. So if we could move P3 up to here and move this new process up to there, then we can coalesce all the externally fragmented blocks and perhaps recover that significant amount of memory for some other process to be loaded. But what's the problem with doing that? Yeah, that's right, heaps of overhead. Not just a little bit, heaps of it. All right, so we've got a fixed partitioning scheme that can lead to internal fragmentation, and we try and circumvent that by coming up with a dynamic partitioning scheme, and that works for a while. It certainly gets rid of internal fragmentation, but results in external fragmentation. What we normally end up doing is using caging and segmentation, which is like a derivation of both approaches. And we put up with a little bit of internal and external fragmentation. So even though, as I mentioned before, this chapter 8 talks about old school memory management, there are still some hangovers, there's still some residual characteristics that present in those that still appear in modern memory management schemes. Okay. Given 5 memory partitions, 100K, 500K, 200K, 300K, and 600 in that order, how would the first bit, best bit, and worst bit algorithms place processes of 212, 14, 417, 112, and 420? And which algorithm makes most efficient use of memory? All right. So we've got a fixed partitioning scheme, and we've got partitions of 100K, 500K, 200, scale. 300 and 600. Right, so these are our memory array with fixed partitions. How would the first fit, best fit, and worst fit algorithm place 212? So I'll list them up here. 212 is the first one. 417. 412. And 426. Okay, first time round, we've got first fit. Remember, the first fit scheme uses a pointer to point to the first unallocated partition, and then it moves down to the next unallocated one, find out whether or not it's big enough to support the process. If it is, it's allocated. And then the pointer moves to the next free partition and stays there. So the next one we search not from the beginning again, but from the current location. That's how first fit works. All right. So if it's first fit, we're going to place the 212K process in the 500K partition, with our pointer resting there at the 200K partition, and then the 417K process, of course, will end up being deposited down here. And our pointer of free to the next free partition goes back to the top. And then we're after a 112K partition. That one's not going to fit, that one's already allocated, so we're back down to here. So we'll put the 112K process there, and then there's no room for the 426K process at all. So using first fit, those were the allocations. All right, what about with best fit? So best fit, we're going to put the 212K process down here, obviously, and the 417K process here, and the 112K process there in the 200K partition, and the 426K process down there. So they'll at least all be memory resident with best fit.
With that option,
Yep.
does it? Is there any preference as to where the 417 and the 426 go?
No, there's not. And the only reason we come up with a unique solution there is because it says they arrive in that order.
Oh, okay.
Yeah. But otherwise, no, it wouldn't be a preference. Alrighty. And then worst fit. Alright, with worst fit, we're looking around for the largest partition for the smallest process. So for the 212K process, we'll put it down here in the 600K partition. For the 417K process, we'll put it there in the 500K partition. And for the 112K process, we'll put it here in the 300K partition, with of course the 426K one not being resident again.
So,
Yes,
what
mate.
strategies
Well, that's a good question. Would you ever use it? I'll tell you what, you would use it under two circumstances only. One theoretical and the other one practical. Theoretically, you could use it to determine whether or not some other candidate allocation scheme had a performance that was better than worst fit. Right, so you'd use it as a baseline in that respect, only to see if some other scheme was sufficiently better. But there's another way in which worst fit might actually be useful. Can anyone imagine what it might be? It gets back to this previous question here. Worst fit might be useful if we're using dynamic partitioning. Does that make sense?
There's more space left over.
Yeah, that's right. More space left over. Yeah, that's right. More space left over, more often,
Small hole, maybe
which might actually be large enough to be useful.
And then that last bit's still completely useless.
So yeah, there might be those rare occasions when it's more than just some stupid academic exercise. Worst fit. Righty-ho.
Because then it will just take effect on needed space, leaving more space to try and fit another place.
Okay.
Because once the partition
Next one is 820. Consider a paging system with a page table stored in memory. Oh, maybe I should Alright. So, 820. Consider a paging system with a page table stored in memory. If a memory reference takes 200 nanoseconds, how long does a page memory reference take? And if we add translation look-aside buffers, what the hell are they? What's a translation look-aside buffer? Sometimes goes by the name of associative memory or associative registers. And what's that? That's just a wanky way of saying a cache. High-speed cache. Alright, so if we've got a high-speed cache and 70% of all page table references are found in the cache, what's the effective memory reference time? Assume that finding a page table entry in the cache takes 0 time if the entry's already there. In practice it takes a little bit of time, but not much compared to a memory access. That's their justification for saying it takes 0 time. Alright, so back to part A. If a memory reference takes 200 nanoseconds, how long does a page memory reference take? Answer?
400.
400. Yeah, correct. How do you get that?
Multiplied by 2.
Yeah, why? It's definitely multiplied by 2.
You got to do the page lookup, followed by looking up the actual address.
That's right, mate. Yes. We've got to take 2 memory references. One to get the information we need to get the second one. And if the page table is stored in memory, we need to go to memory to find the data that we need to work out whereabouts the real physical memory location is. And if it takes 200 nanoseconds to do a memory read, it's going to take 400 nanoseconds to do a complete reference. 2 separate reading operations are required. And that'll wipe a smile off our faces, won't it? When our PC starts running half as fast as we used to. So the solution is to introduce associative memory or associative registers or a translation look-aside buffer. And it says if we add that, let's look at the risk. We add that, and 75% of all page table references are found in the translation side buffers. What's the effective reference time? How do we work out what the effective access time is then? Effective access time. So 75% of all page table references found in the translation book side buffer. So that means 25% of the time we've got a 200 nanosecond time penalty. Yeah? But the 75% of the time we've got a 200 nanosecond penalty plus another 200 nanosecond penalty. Is that right? Is that right, or I just make it up? Try and trick you.
Almost. You also need how. Oh no, it's at 0, so yes.
Critically analyse that expression. Tell me whether you think it's right or wrong.
I'd say it's right, but only because they said TLB takes time if it's there, and they don't give us the time for if it's not there, which technically you'd have to add.
I think you're right. Yeah, yeah. It's close, but no cigar. "75% of the time."
Oh, did I say that?
Yes.
I went the other way around.
That's
Sorry,
right.
I was going off what I wrote down. I thought you'd written it down the right
Yeah.
way.
75% of the time, we've only got a 200 nanosecond time penalty. 25% of the time, the information we need is not in the TLB, and it means we've got a 400 nanosecond time penalty.
The memory,
Is that more reasonable? Yes, I think so.
Is that
Yes,
kept for
that's right.
one of those people?
Yeah. That's exactly how it should be.
No, I thought he just wanted to do
As our
it.
percentage of page hits goes towards 100%, the total amount of time taken, the effective access time, should decrease.
75% of the addresses.
All
Still
right.
in the TLB. 25%, you have to do a paging. That's why it's 400.
823, consider the following segment table. Oh yeah, they're all up formatting a bit here. That should be 90 there, another 100 should be there, and this shouldn't be here, and that should be there. I noticed they fixed that in the next edition. Maybe the family recently introduced it. All right, so considering the following segment table, what are the physical addresses, the following logical addresses? How does this segmenting stuff work? What makes it different to paging? Sorry, mate? Yeah, that's right. And what was the reasoning behind that? With paging, we make an arbitrary choice. Well, it's not an arbitrary choice, it's a design time decision. But we make a choice about how big the pages are going to be and how big the page frames are going to be, so exactly the same size as the pages, and then that's it. all processes get chopped up into pages, and all memory gets chopped up into page frames. And we end up with a tiny little bit of internal fragmentation, but only ever in the last page frame for a particular process. And that works. But with this segmentation, we've got different size blocks. And what was the rationale behind that? Chopping memory up into equally sized blocks, that's going to make the arithmetic nice and easy.
Because you would already have references for all the locations, because you just have to remember, like, because they're all fixed length, you already know.
That's with paging, yes, that's right. It makes the arithmetic nice and easy. But with segmentation, we've got different size blocks, so things are a little bit more complicated there. And why do we do that? Why do we make things a bit more complicated? What's the advantage in doing segmented memory?
Stops, like it makes better use of memory. Because you're only allocating the size required.
Yeah. It's because we look at the layout of the process image when it's in memory, and we chop it up into blocks that correspond to its internal structure. That's the reason that we do segmentation. So we look at the process and we say, all right, this region of that process is instructions. Instead of chopping that block up into lots of little tiny blocks, let's just treat that as one block. Because logically, the information that's in it is separate and distinct from the other information in the process, which is memory, variables, and stack, and other stuff. So we chop the process image up into blocks that correspond to the information that's contained within them. So one block for instructions, another block for the stack, another block for a data segment. And that turns out to have advantages when it comes to sharing that memory between processes. Because if we want to share all the instructions that one particular process has with another process, so that they can concurrently execute the same program, we've only got two addresses to worry about: the starting address of the segment full of instructions and the ending address. Whereas if we're using paging, we've got a whole range of addresses to be concerned about. Because the block of instructions will extend over several, maybe dozens, perhaps even hundreds of page frames. So we've got a lot more, we've got many more addresses to be concerned with in working out the starting address and the ending address of the block of instructions if we use paging instead of segmentation. Same thing if we want to just share a region of memory, or rather if we want to share a region of data that one process has with another. So if we've got a shared memory scheme for exchanging data between two processes, again, with segmentation, we know the starting address and the ending address just of that segment, the data segment. And it's much easier to ensure that processes only access addresses, physical addresses in that range, rather than if we've got a paging scheme with lots of addresses. All right, so that's what segmentation is all about. And this problem says, consider the following segment table. What are the physical addresses for the following logical addresses? So we've got to pretend to be the memory management unit now. And obviously these ordered pairs down the bottom here represent the segment number and the offset. So with A, we've got 0 and 430 being the logical address. That corresponds to a base address of 219 plus the offset, which is 430. So the physical address is 649. So memory location 649. next one is segment 1, offset 10. About base address for segment 1 is 2300. The offset is 10, so the physical address is 2310. The next one is segment 2, offset 500. What does offset really mean? That's right. Distance, it means distance into the segment from the segment beginning. That's what the offset means. Yeah. That's right. Okay, so 2, 500. We've got a base address of 90 and an offset of 500, which unfortunately results in a segmentation fault. Because the question is telling us the segment is only 100 bytes long. If we've attempted to generate an address which is 500 bytes from the start of the segment. If the segment's only 100 bytes long, then we've got a segmentation fault. So the address 2, 500 will be the logical address, that is. 2, 500 will be taken by the memory management unit, and it will be evaluated, and then it will generate an exception that goes back to the processor, so they halt this process, terminate this process, because it's attempted to access an address outside of the range, out of bounds. All right, D is 3400. So now we know what we're doing. We're paying more attention to this column here, aren't we? The length column. Yes, we are. All right, 3,400 means a base address of 327 plus an offset of 400, and now we're checking to make sure that it's less than the length, which it is. So there we haven't got a problem. That's a valid physical address. And then finally 412, 1952 plus 112, bad news again. Someone's been fiddling around with pointers and they don't know what they're doing. All right. Okay, to finish up with 3 problems from chapter 9, 921. Unfortunately, spans 2 pages. Yeah, there we are. All right, so 921. Assume that we have demand page memory. Page table is held in registers. Here we are. Translation look-aside buffer again. It takes 8 milliseconds to service a page fault if an empty page frame is available, or if the replaced page is not modified. And it takes 20 milliseconds if the replaced page is modified. Memory access time is 100 nanoseconds. Assume that the page to be replaced is modified 70% of the time. What's the maximum acceptable page fault rate for an effective access time of no more than 200 nanoseconds? How are we going to deal with that? Who's got some ideas? So we're being asked to work out an effective access time as a function of the page fault rate. Right. 200 nanoseconds is our permissible effective access time. That's our starting point. What do we do next? Okay, well, we're going to end up with an expression that's going to have two parts to it.
Page 4, 30% of the time, please.
Yeah. Yeah, that's going to come into it. Correct. All right, the same. The page table held in registers contains 8 milliseconds to service a page fault if an empty frame is available or if the replaced page is not modified, and it takes 20 milliseconds if the replaced page is modified. So if we've got a page fault, then we've got a certain penalty.
So it would be 20 plus 8. That's page 4.
Yep. Yeah. If we do have a page fault, we might have to replace the page, and we might not have to. So we do have a page fault. Replace page. Or we do have a page fault, don't replace page. It says, assume that the page to be replaced is modified 70% of the time. So 30% of the time, we've got a page fault that we don't need to replace the page for. What can determine whether or not the page has to be replaced? Why have we got 8 milliseconds to service a page fault if an empty frame occurs, or 20 milliseconds under other circumstances? Why is there time difference there?
Because you've got to replace the existing one with...
Yeah, that's right. But there are times when we've got to replace the existing one that involves copying the existing one out to memory, out to virtual memory. And there are other times when we don't have to copy the one that's currently in memory out to virtual memory. What causes those two differences? load a page into memory and there's no free page frames, we've either got to find a page that's currently in memory and copy it to disk to free it up so the new page can be copied in, or we can just find a page frame that's already got a page in it and just overwrite the page which is currently in without copying it out to disk first. Under what circumstances can we do the latter, which is obviously going to take less time? Sorry?
It's just not.
It's not used?
Yeah.
Well, some process will have been using it, otherwise it won't be in there in the first place. But there'll be some times when we've got to copy that page out to disk before we can overwrite it, and there'll be other times we can just say, no, we don't have to, just overwrite it in memory. What causes those two different scenarios?
It's like a fork or something.
It's when the information that's in the page that's currently in memory that we've chosen to be overwritten hasn't been modified since the last time it was copied into memory. That means somewhere on disk there'll be a copy of it which will look exactly like the copy that's currently in memory. So we don't have to copy it out of memory back to disk. We can just overwrite it. So they're saying here, it'll only take 8 milliseconds to service a page fault. If an empty frame is available, which is the preferable scenario, if an empty frame is available, or the replaced page is not modified. So if it hasn't been changed, if the information in that page hasn't been changed since the last time it was copied into disk, then we don't need to copy it back out again because there'll be a copy on disk somewhere that's the same as the current copy in memory. If there's some data in it though, and it's been modified since it was last copied into to memory, then it takes 20 milliseconds to deal with the page fault because we've got to copy the stuff that's in memory to disk first, and then overwrite it. That once again is a good reason to keep tabs on pages that contain instructions as opposed to pages that contain data. Why?
So you don't lose modified.
Yeah, instructions don't get modified. A compiler converts the high-level language into a low-level language, and that gets converted into a machine code and then stored on disk. That's the instructions. They get copied into memory, and they don't get changed. We simply point the processor at them and say, there, instructions, go for it, and it does. It fetches and decodes and executes them. The data modification takes place elsewhere. We've just got a block of instructions that haven't been modified since the compiler finished producing the executable program. So if we've got pages that we know, or segments that we know only contain instructions, they're good candidates for overwriting because we know we don't have to copy them from memory back to disk before we overwrite them. That's why in some instances it will take 8 milliseconds to deal with the page fault, in other instances 20. We resort to the 20 when we can't find a page frame that hasn't been modified since it was last moved into memory. All right, I'm going to put up the answer and then I'm going to explain to you how it appears. There's the answer. And as I said before, it comes in two parts. There's the time penalty when we have no page fault. And if P is the page fault rate, then 1 minus P is the rate at which we have no page faults. And when we don't have a page fault, we've simply got the 100 nanosecond memory access time. That's a time penalty. So that's the simplest scenario. So that's no page 4. The term on the left, 1 minus p times 100 nanoseconds. Over on the right, we do have a page 4. So we've got p outside of some other term. But that other term is internally made up of 2 separate possibilities. Either the page has been modified, or the page is free or hasn't been modified. And we're told in the question that 70% of the time the page has been modified. That means 30% of the time either the page frame is free or the page hasn't been modified. So we've got 0.3 times 8 milliseconds plus 0.7 times 20 milliseconds. All multiplied by p, the page fault rate. What do we do next? We make p the subject of that expression and try and work out what value p should be, what fraction of all physical memory address resolutions, what fraction of all physical memory address resolutions can represent a page fault if we want our total memory access time to be on average 200 nanoseconds, as opposed to the 100 nanoseconds that the electronics service should take. So we make p the subject. It turns out to be something like 1 in 6 million, something like that. 0.000006. Or it might be another 0.6. I don't know. Doesn't matter. Don't care. That's the important thing. Writing down that expression there. And being able to describe why the 3 terms are there, what they mean. That makes sense? So we've got a memory reference taking place, and there's either a page fault or there's no page fault. And if there's a page fault, there might be a 20-second penalty, or there might be an 8-second penalty. That's it. So we write down those 3 possibilities as a function of p, page fault rate, and we can work out what p is if we're really interested. Okay. Crashing. Has the system detected? If in fact it does. Once it does detect it, what do we do about it? All right. So what's crashing? What we did to it here last night. I mean that in the nicest possible way. Just as long as the secretary don't come in, it doesn't matter now. There's our answer. What's going on there? You don't see this happen much anymore, but it used to in the bad old days. You try and run an operating system like IBM's OS2 in 4 megabytes of memory, or even Windows 95 when it first came out. They said the minimum configuration is 4 megabytes of memory. You try and run too many processes, and what happens?
I don't think you could run more than 2.
Take all the resources.
Yeah, things start slowing down really quickly. Interactively, things start slowing down really quickly. And what's the cause of it all?
Not enough resources.
Starvation.
Yeah. Yeah, that's right. We get
Excessive swapping. It's just too many resources being added. So is it
Starvation.
we get the memory management unit
Swapping, excessive swapping.
working really hard, but the processor not working very hard. That's bad. It occurs if we've got too many portions of too many processes in memory.
Let's just dump it.
Not quite enough of each of those processes to be able to sustain execution for very long before a page fault occurs. So the scheduler looks desperately for a process to run, and it starts running one, but then a fraction of a second into the time slice that it's got for execution, it generates a page fault. So it goes straight off to a blocked queue while it waits for the hardware to catch up, and the scheduler finds another process to run, and it starts running that one, same thing happens again. And repeatedly, this pattern of behaviour continues. And so what we can see is the CPU utilisation increases sort of linearly while we increase the number of processes. And then we get to a point where not very much CPU utilisation occurs because the processor doesn't run a process for very long before a page fault occurs. And so we've got loads of I/O going on between memory and disk. That's what thrashing is, trying to run too many processes. And what do we do about it? We either install more primary memory or we reduce the amount of multi-programming that we do. In other words, we kill a few processes. That's it. That's all we can do. Okay, 936. Assume there's a 1024 kilobyte segment. We're talking about something with limited memory capability here. Not that that really matters. A 1024 kilobyte segment where memory is allocated using the buddy system. Using figure 927 as a guide, draw a tree illustrating how the memory requests are allocated. And it's got a whole bunch of requests for them in the sequence there. And then it's saying update the tree as some of the processes release memory that they've requested that have been previously granted. So they want us to draw a tree diagram similar to figure 927. We should have a look at figure 927. Get a bit of an idea of what it is we're talking about. Oh yes, there we are. Buddy system allocation. Oh, I think we can handle that. Where does this buddy system thing come from though? What's the why does the buddy memory management scheme even exist? Where does it come from? How does it justify its existence? Nobody knows? scheme for memory management that works well enough, if we've got to do memory management algorithms in software instead of hardware. And normally we've got a hardware memory management unit. In the bad old days, it used to be external to the processor, and you'd have to interface with it yourself, usually on the main board of the computer. These days, it's a part of a chipset, along with a whole bunch of other devices, all integrated into the microphone, so we don't have to worry about it. We've got a hardware memory management unit there, and it can do the, well, what is it that memory management units are supposed to do? What's their job in one sentence? Yeah. Yeah. Convert logical addresses to physical addresses. That's what their job is. And because the algorithms are quite simple, just add two numbers together and see if it's bigger than some other number. In the simplest case, that's all it does. Add an offset to a base address and make sure that's less than some limit. Because the algorithms they need to execute are quite simple, it's easy to integrate them, implement them in hardware and get them to run at quite high speed compared to a software implementation. But occasionally we'll be dealing with microprocessors or embedded systems often that don't have a hardware memory management unit. And in that case, we have to deal with memory management, the conversion of logical addresses into physical addresses, using a software algorithm of some sort. And the one which is generally favoured is this buddy scheme, because it uses a binary tree, and we know a fair bit about binary trees as data structures, and we can generate, we can look up what else already doesn't work, optimised algorithms for searching through binary trees and adding nodes and deleting nodes from binary trees and doing all the sorts of other stuff that you have to do with them. So we've got about 40 years of computational research and development that provides us with optimised algorithms for doing that. And that means it's possible for us to come up with schemes that are as good at runtime performance as we can expect, given that we have to do memory management in software instead of hardware. That's the approach. If you use the special sawn-off version of Linux for microcontrollers, it doesn't have a requirement for a hardware memory management unit like the normal desktop or server version of Linux does. And the scheme it uses is this buddy scheme. So if you put Linux on a 32-bit microcontroller, and that microcontroller doesn't have a hardware memory management unit, then this will be the way in which memory management is done. All right, let's see it working. So we've got 1,024 kilobytes of memory total. And the first thing that happens is there's a request for 240, it says 240 bytes in the question there. We're going to assume they mean 240 kilobytes, or within that person. A hell of a hundred tree. 240 bytes. Well, the first thing that the buddy scheme does is it splits the entire memory array into two 512K buddies. We'll just assume that I'm putting K there where we've got units are Ks. Kilobytes. So we split the 1,024 memory array into two 512K buddies, and we split the two 512K buddies into two. Well, we split one of them into two 256K buddies, and then we stop at that point, because the request is for 240K. And 240K is between 256 and 128. So what we'll do is we'll give that entire 256k block there to this process that requires 240. And of course we're losing a little bit of memory there due to internal fragmentation, aren't we? How much are we losing?
16.
Yeah, 16k. Oh well, tough. That's what we say. Another process comes along and wants 120. So we'll split this into two 128k blocks. And we'll give the process that wanted 120 one of those. Then someone else comes along wanting 60. So split the remaining 128k block into two 64k blocks. And allocate 60 there. And then another process comes along wanting 130. So we go back up here to this 512k block, which has been sitting there
Can't just split to 56.
waiting for us. Split into 256k buddies. And we give one of those. So we've got a fair bit of internal fragmentation wasted there. 130. So that's the state of it. And we can see that the blocks of memory in pairs are always half the size of the parent block. So two buddies always have a parent which is twice their size. Different by a single power of 2, of course, in magnitude. And that results in a division by 2, which is a very simple arithmetic operation, isn't it? Division by 2 in binary, how do we do that? Division and multiplication are usually expensive operations, arithmetically. They're not when we're dealing with powers of 2, are they? That's right. If we want to divide a number by 2, it's just an arithmetic right shift by one bit position, and one instruction. That's it. So that's why this is the scheme which can be implemented with a modest amount of computational overhead. All right, well, that's half the question done. The second half says, modify the tree for the following releases. It says, perform block coalescing wherever possible. What does coalescing mean? That's right, join up. All right, so release 240 bytes. That means that this block now becomes free. So that one is now free. We can't do any coalescing because its buddy is actually being used. Its buddy's being split. It's being used, so we can't do any coalescing at the moment. Then we release 60 bytes. So that one becomes free. And that means we can eliminate those two blocks there altogether and coalesce them and reproduce that 128k block there right at the top of the pen. So they get joined together. And again, that's a really easy operation to do if a binary tree is the construct of mapping all of these blocks. Then we release 120k. So this process here finishes, or it finishes with the memory anyway. So we coalesce those two, and then we coalesce those two, so they disappear. And we just end up with that 512K block there. So those elements get pruned off the tree, and our tree looks like that. Does that make sense? All right. So that's practically that. We've done tutorial properties from 1, 2, 3, 4, 5, 6, 7, 8, and 9. Yeah. So next week there's a public holiday. You'll have plenty of time to look at the lectures. We'll probably hear some like chapters 10 and 13. And then in a fortnight's time, we'll do those tutorial problems. Once the chapters 10 and 13. 6 of them all together. And then we're done. We'll do any of the tutorial problems that we've looked at.